Hi and welcome to Similarity Video 2. In this video we're going to consider some theoretical and contextual applications of similarity. And I've got for you 3 examples to consider. The first example looks like this. Find and demonstrate the similarity in the following diagram. So we have 5 labels of corners or vertices and we have 2 triangles. Sometimes the best thing to do is to start by actually just sketching out the 2 triangles separately. Now there are some statements I can make about these 2 triangles. The first is that angle PRT is equal to angle QRS, and the reason here is that this is given. And the second statement I can make is that angle RPT is equal to angle RQS, and these are corresponding angles. And the third statement I can make is that angle RSQ is equal to angle RTP. These are also corresponding angles. So there's my 3 statements, and this gives me that triangle RSQ is similar to triangle RTP due to AAA. So all 3 pairs of angles are equivalent. You'll notice here that we had to use corresponding angles, and that whole concept of angles in parallel lines will be hugely important for proving similarity, something that's worth going over if it's needed. Let's have a look at example 2. In example 2, we're given the idea that a building casts a shadow that is 8.4 meters long, and at the same time, your own shadow is 2.1 meters long, and you're 1.8 meters tall. So here's my diagram. First of all, you are 1.8 meters tall, and you cast a shadow of 2.1 meters. And also the building, which is h meters tall, casts a shadow of 8.4 meters. And so you can take this out and create 2 small triangles from it. I can prove similarity. And I'm just going to write this down for you and you'll be able to follow through it. It looks very similar to the first proof. So now that we've made the proof that angle or triangle ABC is similar to triangle ADE, we can also state that there is an equivalence between the ratios formed by their pairs of sides. So in this case, we can use that to state that DE divided by BC is equal to AE divided by AC, which gives us that H divided by 1.8 is equal to 8.4 divided by 2.1. And that gives us that H is equal to 8.4 over 2.1 times 1.8, which of course is 7.2 meters. This building is 7.2 meters tall. Next, let's have a look at example 3. In this example, we're told that similarity can be used to effectively calculate distances that are challenging to measure, such as a river as an example. Let's say a surveyor starts at point Y, 10 meters from point X on a river, and they measure from point Y to point Z as 16 meters. So let's start making a note on our diagram of these. Y to Z is 16 meters. And using a person on the other side of the river, they can see a direct line of sight from Y to T through X and from Z to B through X. The person on the other side of the river measures B to T to be 24 meters and Y to X is 10 meters. So now we can prove similarity using the following. And through just two angles, we can make the statement that triangle BXT is similar to triangle YXZ as required. And this also means that, as previously, we can now create the following proportionality statements, that YZ over BT should be equal to XY over TX. And I've deliberately done this a little bit more abstractly. When we substitute these in, we'll get 16 over 24 should be equal to 10 over the width of the river, which we'll call W, and I'll write that onto the diagram. And so therefore we can write down that the width times this simplified expression, which is 2/3, 16 out of 24, is equal to 10. And of course that means that we get the width is equal to 10 times 3 over 2, which is equal to 15 meters. So the river has a width of 15 meters. So there you have some examples of how we can use similarity to find missing sides and how we can prove similarity in a range of different contexts. It is really common to be finding or showing similarity through our angle system and then finding a missing side. That is the most common type of context, but there are a whole